In this video, I'm going to walk through the integration process for several different problems. We've learned a lot of different rules: integration by substitution, integration by parts. We've got a power rule, constant multiple rule, integration of an exponential function. So we've got all these different techniques. And so what I'm going to demonstrate is how to solve a wide variety of problems using the techniques that we've covered so far. So I've attached a worksheet for you on our class website, but I'm just going to work through a variety of problems so you can kind of see the reasoning process that goes on when solving these different problems. So the first one is this problem number 1. I've got the integral of 3x squared times e to the x cubed dx. So I'm supposed to find the function whose derivative is this. Well, the first thing I recognize is that this function right here, x cubed, has this as its derivative, the 3x squared as its derivative. So I'm going to use integration by substitution. I'm going to call the u the x cubed. That means that du is going to be the derivative of this, which is 3x squared dx. And now I'm going to rewrite this integral in terms of u and du. So that's just the integral of e to the u. And then the du is the 3x squared dx. So all together, that's the du. Well, I know that the integral of e to the u is just e to the u plus a constant. And then we substitute back in what u was, which is x cubed plus the constant. So there I found the antiderivative of this function, 3x squared e to the x cubed, which is e to the x cubed. All right, let's do problem number 2. Problem number 2 looks like this. The integral of 10 all over 2x plus 1 quantity cubed dx. Well, I observe that the derivative of this quantity in the parentheses is 2. 10 is bigger than that, 5 times bigger than that. But yeah, I can make this work in terms of rewriting this integral using integration by substitution. So I'm going to pick u is equal to 2x plus 1. Du then is equal to 2 dx. Now I've got a 10 up here, so what's the same as 10 dx? Let me multiply both sides by 5. 5 du is the same as 10 dx. So that's going to allow me to rewrite all of this. So I've got the integral of 5 du, so let me put it over there, 5 du all over u cubed. That's also written as 5u to the negative 3 du. I can bring that 5 out in front from our constant multiple rule. And now using the power rule for integrals, I add 1 to the power and divide by the new power. So I get 5u to the negative 2 divided by negative 2 plus a constant. Let's continue over here. That 5 divided by the negative 2, that'll just be negative 5 halves. And then u to the negative 2, but u was 2x plus 1. So 2x plus 1 is the negative 2 plus a constant. Now, you can leave it like this. If you want, you can rewrite it in a variety of ways. Here's one way to rewrite it. Negative 5 all over 2 times 2x plus 1 quantity squared plus a constant. So this form is fine. This form is fine. Any correct answer is going to be fine for that one. All right, let's move on to problem 3. Right, for this problem, I observe that if I let this be my u, x squared plus 9, then the derivative of this is 2x. I've got x up there, so yeah, I can make this work. So let's go and pick u equals x squared plus 9. Then du is 2x dx. But I have an x dx up there, so I need this side to look like x dx. So I just multiply both sides by a half. That makes the right-hand side here equal x dx. Then I'm going to rewrite this whole thing in terms of u. So I've got the integral of, I've got that 1/2. I'll go ahead and put that out here in front of it. I've got the du in the back. That's the x dx part. Then I've got 1 over, there's my u, square root of u. That's the same as u to the 1/2. So I can rewrite this as 1/2 times the integral of u to the negative 1/2 du. So again, I add 1 divided by the new power. That'll be u to the 1/2 divided by 1/2. Well, that's convenient. Plus a constant. Well, those two 1/2s are going to cancel out. That's nice. And that will leave me with u, which was x squared plus 9, to the 1/2 plus a constant. Alternatively, of course, you can write that as the square root of x squared plus 9 plus the constant. Let's just double check to make sure we did it right. Make sure I didn't make any mistakes. Here we go. Check. So I'm just going to start here with the x squared plus 9 to the 1/2. That's going to be my y value. And I'm going to find y prime. So y prime is, bring the exponent down in front, leave the inside alone, drop the exponent by 1, times the derivative of what's inside. The derivative of what's inside is 2x. The 2.5 cancel out, leaving me with x times x squared plus 9 to the negative 1/2. That's equivalent to x all over the square root of x squared plus 9. Which, if I look at this, and compare it to where I started, that's the same value. So I've solved this problem correctly. We're going to dive into problem 4 here. And as in working on this problem, I want you to know it's not always obvious on how to jump into a problem like this. You might have to do some trial and error, like I had to do before I figured out exactly how to approach this particular problem. And so just be persistent. Try different things. If something doesn't work, try something else. And so I'm going to go ahead and work through this. As it turns out, I'm going to use both integration by substitution and integration by parts. So let's start off, first of all, with integration by substitution. And I will go ahead and walk through that. I'll be referring to my notes because I had to work it out separately, do a little bit of trial and error to figure out how to approach this. So here's my strategy. I'm going to do instead of a u substitution, I'm just going to call it x this time, such that when I get down to the integration by parts part, I'll be able to use u and v. So I'm going to say x is equal to t squared minus 4. That means that dx is 2t dt. And another way to write that is 1/2 dx is t dt. All right, it may not be obvious what I'm doing here yet, but let me tweak that slightly, and then you'll see why I'm doing what I'm doing. So I'm going to rewrite this, but I'm going to factor out a t here. When I factor out a t, I have t squared minus 4. Then that t that I factored out, I still have e to the t squared minus 4 dt. But notice what I just created by doing that. I know that t dt is 1/2 dx. That's awesome. This is u, this is my x. And this is also x. So this can be rewritten as the integral of x. And then this t dt is 1/2 dx. I'll put the 1/2 out here in front and the dx back here. And then this is just e to the x. So I've got x e to the x. I can bring that dx back over here. dx. Okay. Now on this part, I'm going to use integration by parts. So I'm going to say let u equals x. Then du is just 1 times dx. Let the dv be e to the x. And then v will also be e to the x. Because the antiderivative of e to the x is e to the x. All right, so I've got this whole integral. Let's see. Make note that I've got that 1/2 out in front. We don't want to forget that. Okay, so this integral is u times v. So that's x e to the x minus the integral of v, which is e to the x, du, which is just the dx there. Well, this is just 1/2 x e to the x minus the antiderivative, that's e to the x, then plus a constant. Or in other words, if I just factor out the e to the x there, it's just 1/2 e to the x times x minus 1 plus c. All right, well, what was x equal to? Well, x is equal to this. Let me go ahead and put that in. So it equals 1/2 times e to the t squared minus 4 times the quantity t squared minus 4 minus 1 plus the constant. Or in other words, 1/2 e to the t squared minus 4 times t squared minus 5 plus a constant. Okay. So not trivial. That was a fair amount of work to get to the antiderivative. And you might be asking yourself, is that truly the antiderivative of that integrand? Well, let's convince ourselves. So I'm just going to say y equals that loveliness, 1/2 e to the t squared minus 4 times the quantity t squared minus 5. That's my function. I'm going to take the derivative of this function, and if I do it correctly, I'm hoping it will equal that. So y prime is, we're going to have to use the product rule. This will be my first function. This will be my second function. So the derivative of the first, it's going to be 1/2 e to the t squared minus 4 times the derivative of what's in that exponent, which is 2t. So the derivative of the first times the second, which is just t squared minus 5. And I'm going to have to make myself some space. So that was the derivative of the first times the second, plus the derivative of the second, which is that, which is just 2t, times the first, 1/2 e to the t squared minus 4. And so there it is, product rule. So let me see if anything nice happens. Well, this 1/2 and that 2 cancel out. That's nice. I can go ahead and distribute this t through there. So I'll go ahead and do that. So I get e to the t squared minus 4 times t cubed minus 5t. So that's what I've got on that piece. Over here, the 2 and the 1/2 are going to cancel. I get a plus here, and so those are canceling, plus t e to the negative, rather not negative, to the t squared minus 4. And I observe that both of these terms have a e to the t squared minus 4. So let me go ahead and factor that out. So I get e to the t squared minus 4. Here I've got t cubed minus 5t. Once I pull this out, I'm left with a plus t. Well, I got minus 5t plus t, so that would be minus 4t. So e to the t squared minus 4 times the quantity t cubed minus 4t. And I'm looking up here, and I'm hoping it looks the same. T cubed minus 4t, there it is. E to the t squared minus 4, there it is. I've done this problem correctly. Okay, that was a little bit of work. Next, we'll move on to problem number 5. Problem number 5 is just this one. The integral of ln of x dx. And we may have done this one in an earlier video. I think we did. I will do it again, just in case. And on this one, I'm going to try to use integration by parts. And I'm going to set it up like this. I'm going to let my u be the natural log of x, and my dv be dx. Well, the derivative of u is just the derivative of the natural log of x, which is 1 over x dx. The function whose derivative is, there's really a 1 there, right? This 1 is just x. So v is equal to x. So by integration by parts, I've got u times v. So this integral is going to equal u times v. That's going to be x times the ln of x, minus the integral of v, which is x, times the u, which is 1 over x dx. Well, that's nice here because the x's will cancel. So this is x ln of x minus the integral of 1 dx. Well, the integral of 1 is just x. So this is equal to x natural log of x minus x plus a constant. If you want, you can factor out the x and get x times the natural log of x minus 1 plus a constant. So you can leave it here if you want, or you can leave it in this form. Either way is fine. All right. Again, I can check my work by taking the derivative to confirm that I got it correctly. I'm confident with what I've done. But let's just double check just in case. Check. I'll check from here. Check. So I'm going to do y is equal to x natural log of x minus x plus the constant. All right, y prime. Derivative of the first is 1 times the second, which is natural log of x, plus the derivative of the second, which is 1 over x, times the first, which is x. And then times the derivative of this is minus 1. And then derivative constant is 0. So let's see what we've got. ln of x plus, well, x over x is 1, minus 1, plus 1 minus 1 is 0. That just gives us ln of x, which is the integrand we started with. So yes, I did it right. Let's now move on to number 6. Number 6 is this problem. Integral of x e to the 5x dx. All right, how should we approach this one? Well, let me try integration by parts again, with u being equal to x, dv equals e to the 5x. Let's see what happens. If u is equal to x, then du is equal to dx. And the function whose derivative is e to the 5x is 1/5 e to the 5x. We can verify that. The derivative of e to the 5x is going to be 5e to the 5x, but when multiplied by the 5th, that gives us just that. So that integral up top is equal to u times v. So that will be that 1/5 x e to the 5x minus the integral of v du. So that's 1/5 e to the 5x dx. 1/5 x e to the 5x minus 1/5. All right, what function has this as its derivative? Well, that will be e to the 5x all over 5 plus a constant. So I get 1/5 x e to the 5x. So 1/5 there, dividing by 5, that's going to be 1/25 minus 1/25 e to the 5x plus our constant. There it is. All right, there it is. I'm going to go ahead and initially rewrite this. I want to write this as the integral of 1 over x times 1 over ln of x dx. I just broke that apart, slid the dx off over here, rewrote it as 1 over x and 1 over ln of x. U is going to be the natural log of x. Du, the derivative of natural log is just 1 over x dx. The good news is, I see that right here. 1 over x dx. There it is. That's the du. So what I'm looking at here is the integral of 1 over u du. So I want to know the function whose derivative is 1 over u. Well, that function is the natural log of the absolute value of u plus our constant. So the natural log of the absolute value of u, but u was the natural log of x plus a constant. So it's a little wild and crazy here. The natural log of the absolute value of the natural log of x plus constant. All right, now we'll move on to number 8. So we're going to use integration by parts on this one. We're going to have to apply integration by parts twice to get this term down to a constant. So that'll be fun, a little bit of an adventure. Let's let u equal to x squared and dv be e to the x dx. Of course, then v is e to the x. That's nice. Derivative here is 2x dx. So what we've got, let's go ahead and put our pieces together. We have that integral is equal to u v, so it'll be x squared e to the x, minus the integral of v du. So that's 2x e to the x dx. Well, now I'm going to have to figure out this integral using integration by parts itself. So I'm going to pick my u equal to 2x, my dv equal to e to the x. Of course, then v is equal to e to the x. du is the derivative of this, which is 2 dx. So now I'm going to rewrite that with this. So let me keep bringing this down. X squared e to the x minus this whole parenthesis thing's okay. uv, that'll be 2x e to the x minus the integral of v, which is e to the x du, which was 2 dx. So let me see if I can integrate that. So let me go ahead and write this out. X squared e to the x minus 2x e to the x. This minus and that minus are going to be a plus, and then we've got that 2. So I've got plus 2. And the antiderivative of e to the x is, in fact, e to the x plus a constant. Now, if you want to, you can factor out that e to the x. This is just e to the x times the quantity x squared minus 2x plus 2 plus a constant. Kind of crazy, this mess has a derivative of x squared e to 2x. Suppose you weren't convinced of that, though. Let's check. Let's convince ourselves that that is in fact the case. So let's let y equal this. Plus our constant. Let's just go ahead and find the derivative of that using the product rule. Y prime, derivative of the first, e to the x, times the second, which is this, plus the derivative of the second, which is going to be 2x minus 2, times the first, which is e to the x. Derivative of our constant is 0. Let me go ahead and factor out the e to the x and then just combine my terms. Y prime equals e to the x. I've got x squared minus 2x plus 2 plus 2x minus 2. Well, what happens here? The 2 and the minus 2 cancel. The negative 2x and the 2x cancels. All I'm left with is x squared. So I've got e to the x times x squared, which you can alternatively write as x squared e to the x. So we did it correctly. Now we'll go on to number 9. Look at the integral of x ln of x dx. All right, how might we want to approach this? Well, we'll try this. Let's let u equal ln of x. We'll try this. And then dv is equal to x dx. So du is equal to 1 over x dx. V is going to equal 1/2 x squared. So this integral is going to be equal to 1/2 x squared times ln of x, that's our uv, minus the integral of v du, 1/2 x squared times 1 over x dx. That's 1/2 x squared times the natural log of x. I'll bring that half out in front. The x squared times the 1 over x is just leaves me with x dx. And I know how to integrate that. So this is 1/2 x squared natural log of x minus 1/2, add to the 1 to the exponent, divide by the new power, plus a constant. So all together, that's 1/2 x squared natural log of x minus 1/4, because the 1/2 divided by 2 is 1/4 x squared plus constant. All right, let me convince myself that I did it right. So y is equal to 1/2 x squared natural log of x minus 1/4 x squared. So y prime equals, and we don't have to use the product rule here. Do the first. Well, that's going to come down. That's just going to give me x times the second plus the derivative of the second, which is 1 over x, times the first, which is 1/2 x squared, minus the derivative of this, which is 1/2 x. So let's see what happens. I've got an x natural log of x. I've got 1/2 here, but then x squared divided by x, so this is just going to be plus 1/2 x minus 1/2 x. Those two quantities cancel, leaving me with x natural log of x, which was the integrand. Problem 10. I've got the integral of t e to the 3t dt. So I'm going to let u equals t and dv equal e to the 3t. So du is going to be dt, and v is going to be e to the 3t times a third. So now put the pieces together. T times v, or u times v, is going to be 1/3 t e to the 3t minus the integral of 1/3 e to the 3t dt. That's our v du. And I know how to integrate that. So this is 1/3 t e to the 3t minus 1/3. The antiderivative of that we just did a moment ago is 1/3 e to the 3t plus our constant. So I get 1/3 t e to the 3t minus 1/9 e to the 3t plus a constant. Now moving on to number 11. Number 11, I have x cubed e to the x squared dx. This looks very similar to a problem I did earlier. It's very similar to problem number 4. So I'm going to consider a similar strategy. So let me try this. I'm going to call it t this time, t equaling x squared. If that's the case, then dt is just 2x dx. I'm going to try to rewrite all of that in terms of t. So let me go ahead and divide here. 1/2 dt is equal to x dx. And let me look at this a slightly different way. I've got the integral of x squared times x, that's how we get x cubed, e to the x squared dx. And the reason I broke it up like that is, see, I've got an x dx there and an x dx there. That's going to be half a dt. I've got t, x squared is t, so there's a t. This is t e to the t, then dt. So this integral is t e to the t dt. Now I'm going to be able to use integration by parts. So I'm going to let u equal t, dv equal e to the t dt. So then v is e to the t, du is equal to 1 dt. And I'll set up my integral, u times v. So that's t e to the t minus the integral of v du. So that's e to the t dt equals t e to the t minus e to the t plus a constant. And what was t? T was just x squared. So this is going to be x squared, e to the x squared minus e to the x squared plus a constant. And the derivative of this is that. If you're not convinced, let's prove it. I'm going to call that y. So y prime is what? Derivative of this is just 2x times e to the x squared plus the derivative of the next one, which is e to the x squared times the derivative of the x one, which is 2x times what we have in front, x squared. So this is all the product rule. The derivative of this is just e to the x squared times the derivative of the x one, which is 2x. And the derivative of the constant, of course, is 0. So I've got 2x e to the x squared plus, what do we get here? 2x cubed e to the x squared minus 2x e to the x squared. And certainly this term in front and this term in the back cancel. And I'm left with 2x cubed e to the x squared, which I observe is twice as big as what I was expecting. So did I make an error along the way? And in fact, I did. So let me go and correct my error. Notice here that x dx was equal to 1/2 dt. I forgot the half. So let me fix it all the way down through. I have a half out here in front, half out here in front. And so when I get to this result over here, I'm going to have to multiply this all by 1/2. And so this final answer is going to have to be multiplied by 1/2. And so that means when I get down here to my derivative, that's being multiplied by 1/2. And then that will cancel and I'll get back to where I was at. So if you're like me, you might be human and accidentally from time to time drop something. Like I accidentally dropped that there. But I was able to detect my error here at the end by checking, oh, I made a mistake. Where was my mistake? And I went back and I was able to find it. So definitely recommend, especially in an assessment situation, absolutely check with the derivative, because then you might catch your own errors like I just found. And the final problem for the day is problem number 12. And it's like this. The integral of 2x plus 5 e to the x squared plus 5x dx. So I've got u is equal to x squared plus 5x. Du is equal to 2x plus 5 dx. And this is going to be just a straightforward integration by substitution. So I noticed the 2x plus 5 dx, that's what du is. So this is just the integral of e to the u du, which is just e to the u plus a constant, which is e to the x squared plus 5x plus a constant. And there we've done it. All 12 problems. Have a great Thanksgiving.